My name is Professor Duke Orata. We have been having lectures and we are continuing our lectures. Today we will look at irreversible adiabatic flow in ducts of varying areas. Flow duct of varying area. Now, this is very, very important for us, and I believe you are going through our other lectures because we are building our concepts systematically. So we are going to look at reversible adiabatic flow in a duct of varying area. So the profile for this particular flow can be captured in this schematic, which we have seen in the past. We are dealing with ducts of varying area. So we have flow axis, so we have pressure, and then, of course, remember we are dealing with an infinitesimal segment, and we have C plus DC, so it's infinitesimal changes, A plus dA, that one be D for subscript S. Now, this is a duct of varying area, and we are talking of a reversible flow. And so it means that there are frictional forces involved as a result of shear stress along the wall. So we can show that. Our forces. So we have shear stress, which of course is opposing the motions, so that tau is shear stress. So we are saying we have frictional forces as a result of shear stress along the wall. And if you remember, our notation for shear stress was tau. Very, very important for us to note that. And so what does that mean? What is the frictional force involved? So the frictional force in this particular case will be the shear stress times that chain there. And so if you look at it, that opposing force in this axis here, that is the axial direction, the opposing force in the axial direction in the axial direction can be computed, therefore. Let's call that theta. Let's call that theta. That opposing force in the axial direction, therefore, will be given by tau, yes, cosine of theta. And this basically is tau dA, cosine of theta, over sine of theta. And of course, from simple trigonometry, you know that is basically tau dA cotangent of phi, or what I've called theta or phi. I've denoted as that. Theta normally denote theta as that. Let's just say that is as phi. So we are saying that the frictional force that frictional force in that axial direction is the shear stress, and that change in area cosine of phi, that is basically the same as tau dA cosine of phi over sine phi, and of course from simple trigonometry that is called tangent of phi. And so when you remember what we did the very first time, then the total force here, we can reflect that as we have ADP plus remember we have we have DC squared over 2. Let's go back first. Remember, we had the sum of all forces acting was given as M C2 minus C1, if you recollect. These were all forces interacting. And so, in this particular case, what are we going to have? We'll again have our ADP. If you remember, we had our ADP because these expressions here we got from P plus dP A plus dP dA, and we had P A, and of course we had that component which was P plus dP over 2 A plus dA, and that, remember, was equals to M dC. Remember that? That was the very first expression which we had. And when we simplified this quantity here, we had actually ADP, remember? We had ADP, and we had plus AC over V dC is equals to 0, and if you recall correctly, that was the continuity expression. And so, in the same token, when moving and factor in the frictional force, so factoring in the frictional force, and again I suggest that you go through our earlier lectures. We sorted this out. We simply opened up PA, then P and A, and that was PA, that was PA, PDA, DP, DA, and then we had for this particular one, PA plus PDA, and then DPDA over 2, and so forth. And we said that those quantities which were doubly infinitesimal of the higher order infinitesimal quantities vanished, because we mentioned that when you multiply smaller quantities, you get much smaller quantities. So the doubly infinitesimal quantities like dA, dP, just to remind you, something like that, that's doubly infinitesimal, is equal to 0. So just open up these full brackets, eliminate the doubly infinitesimal quantities, reorganize your equation, and you'll end up with this particular quantity. So I think this is this we discussed. I think it was the second lecture from this, or the third lecture from this. So you need to look at our earlier discussions so that we are able to work on them. Now, so factoring in the frictional component. So now, when you factor in component, we have minus ADP, remember is opposing in the axial direction, minus AC over V dC minus tau dA cotangent phi, that is equals to 0. Very important equation. That's very important equation for us, because remember, when we are talking of the energy equation, let's just remind ourselves of the energy equation. You have the energy equation. Remember the energy equation. where we have dH plus dc squared over 2 g dz is equals to dq dw, of course, the quantities 0. So what do we have? We have dH plus dc squared over 2. If the datum level is insignificant, that will be 0. So that will be equal to 0. And I always want you to remember, always remember, note that dc squared over 2 is the same as c dc. Integrate these quantities, the same quantity. Of course, using the identity, always remember dn is xn plus 1, n plus 1 plus the integration constant. Always remember that. So this basically is the same as dH plus c dc is equals to 0. Now, if you look at these two equations, they are not the same. These equations are not equivalent. They are not equivalent. Notice that the two equations are not equivalent. But if we were to assume that tau is 0, if we assume that tau is equal to 0, then that will vanish. Then this equation here will be reduced to minus a dp minus ac over v dc is equals to 0. And now you can clearly see that we are headed in that direction. Let us simplify this further. Let us simplify it further. So if we simplify this expression, let us simplify that expression. If we simplify it, let's simplify this particular expression. Can divide by a, if we divide by a and cross multiply by v. So we divide by a and cross multiply by v. What do we get? We will have a will divide that will be minus a will disappear, so we'll have v dp, and of course we will have this particular a will disappear, so we'll have minus c dc is equal to 0, or v dp plus c dc is equals to 0. Now, you remember that if we assume that we are dealing with asymptotic processes, when we're dealing with an asymptotic process, let's just remind ourselves so that you never get lost. When we're dealing with asymptotic process, for asymptotic process, remember that dH is equals to du plus p dv plus v dp. So du, which is equals to dq plus dw, and if you use the Clausius inequality, dq over t, or tds equals dq, we can put in place of dq tds, so we have dh plus is equals to tds plus dw plus pdv plus v dp. Remember that? And what is this quantity? Is minus pdv. So these two will cancel. And if you are dealing with an asymptotic process where there's no change in enthalpy, then you notice that in that particular case, tds will be 0. So dh will be equal to v dp. So that v dp is dh. So since v dp is equal to dh under asymptotic conditions, then we can now have our equation here, which is the energy equation, which we had shown there, that dh plus dc squared over 2 is equal to 0. And remember, we said that is the same as dh plus cdc is equal to 0. So what does that mean to us? So we are saying that these two equations were not equivalent. But if we assume that tau is 0, then you notice that it will reduce to A dP minus AC over V dC, which we have simplified somewhere. We have simplified it, which we have simplified, so we have that expression there. And that expression there, because now dH is the same as VdP, is VdP plus CdC, and this equals 0. So you notice that those two equations are now the same. If you assume tau is 0, and remember tau is the shear stress, so frictional force basically we assume is 0, then the two equations collapse to the same expression. Very important for us to know. Otherwise, you have to bring in the expression for involving the frictional force. Now, this frictional force can depend on several things. The frictional force can depend on several things. It can depend on velocity and turbulence. We have a lot of discussions in our earlier lectures dealing with flow, whether turbulent or streamline flow and so forth, and we looked at various elements and models to discuss those particular things. So I keep encouraging you to look at our lectures and follow them systematically. And also the surface characteristic of the duct. This will affect the frictional force. And so it means that this becomes a very complex situation, especially if the frictional force varies with the duct, with all these particular aspects of the duct. So it means that you have to be able to empirically determine this quantity as a function of these particular aspects of the duct. And so, to make your life easy, when you are designing, for example, a nozzle, then you will concentrate the empirical coefficients which can make your life a little bit easy so that you are able to use that other than trying to determine this force empirically. So you can use frictional coefficients. You can use frictional coefficients to help you in your computations, because if you use those frictional coefficients and you couple it with the continuity equation and the energy equation together with an equation of state, then you can actually compute most of these things. So this complements, if you know the energy equation, you have an equation of state describing your fluid, and then you have your continuity equation, then you can compute these quantities. And some of the frictional coefficients which are used in these computations in design of nozzles, for example, you have the velocity coefficient. Velocity coefficient Kc. And that velocity coefficient is simply, if you will focus on the exit velocity for the nozzle vis-a-vis that velocity under isentropic conditions. Isentropic conditions. So you can focus on the exit velocity. The other coefficient which can be useful is the efficiency coefficient of the nozzle, which is neta n. And that neta n, the coefficient, the efficiency coefficient of that nozzle is related to the enthalpy drop under those conditions and under isenthalpic conditions. H1 minus H2, and H1 minus H2 under isenthalpic conditions. What does this mean? I want to focus on this because we have discussed it when we were talking about in our very, very earlier lectures on nozzles. I want you to remember that from the energy equation, just remember, the energy equation, we have said dH plus dC squared over 2 plus g dz is equals to dq plus dw. And this should now be an equation which should be stuck in you. Should be something which should be stuck in you, because you have to operate with it. So we know that is 0. Also, when we say that if the datum level is not significant, that would be 0. So dh